Hey class, my name is Mateen. For my project, I wanted to go into the physics associated with doing one push-up. Specifically, I want to go into torque. So first, I need to go a little quickly here, but here's a diagram of the two positions that I'm going to be in. One is the downward position where I'm parallel to the floor, and another one I'm going to have an angle theta with the floor, which is when I'm in the up position, right? So we can use trigonometry to figure out a lot of these things. But first I want to get some of these values down, like some of the ones that I need are the mass of myself, which are 57.6 kilograms, the length of myself, which is 1.72 meters. These are both obtained from the doctor's office, so they're very accurate. I also need the length of my arms, which are 0.5 meters, and the length from my toes to my arms, which is 1.3 meters. These were both using a flexible ruler. So there's some error associated with it, about 0.005 plus or minus meters. So first thing I want to do is figure out the center of masses, which for the first position, there's two different center of masses. The first position is going to be right down the middle because, as we know, for a thin rod, let's say, it's going to be 1/2 L, and the length is 1.72, so 0.86. For the second one, it's a little more complicated because, as you can see, the center of mass is right there, but the x-coordinate associated with it is a few down, right? It's where it's a level with the floor. So to find that one, we have to do some trig. But we can see that the cosine of theta is equal to that second center of mass over 0.86, which is the distance from my toes to the middle right there. So that's going to give us 0.79 meters. So we have that. Next, I want to get the force associated with my arms holding me up in that first position. So as you can see, that's force 1, and that's where my arms are. So we need to figure out the net torque, or the torques that make up the net torque, which are the torque due to gravity minus the torque due to that force equaling 0, because I'm not moving, right? So it's a net torque of 0. So the torque due to gravity is mg x center mass, and the torque due to the force is, since we're perpendicular to my body, you can just say it's the force times the distance. So force times 1.3 meters, right? So when we get the force isolated, it's going to be 373 newtons. So 373 newtons of force is holding me up when I'm in that first position. So just as a quick fun fact, it takes only 9 pounds of force to break a nose. And so 9 pounds of force is about 40 newtons. So would my nose survive if my arm suddenly gave out and I just hit the floor? And the answer is definitely not. And so next, I want to figure out the net torque associated with that one push-up, that motion, right? And I figured the easiest way to do this is to get the torque of gravity at the top minus the torque of gravity at the initial position. So mg x2 center mass minus mg x1 center mass, which comes out to negative 39.5 Newton meters. So I want to point out that this is negative because we're actually moving in the clockwise direction, and the counterclockwise direction is positive. So the torque due to gravity is actually in the positive direction. Now next we need to know the moment of inertia. So since I'm a thin rod with my toes as the end point there, we're going to have I equals 1/3 ml squared. So 1/3 times my mass times my length, 1.72 squared, it's going to come out to 56.8 kilogram meters squared. So from this, I'll be able to find out the angular acceleration. The angular acceleration, as we know, is equal to the net torque over I, or the moment of inertia. So it gives me, so negative 39.5 over 56.8 is going to give me negative 0.695 radians per second squared, is the units we get it in. And from this, we can also get the angular velocity if I was able to measure my time accurately enough. So this is going to be the time from that initial position to a velocity of 0 at the ending position, which I got as 0.6 seconds. So 0.695 radians per second squared over the 0.6 seconds is going to give me negative 1.16 radians per second. So that's my angular velocity. Now I want to check my acceleration, and a way to do that is first we're going to get the tangential acceleration. So we have the angular acceleration, and we have the radius, so the angular acceleration times the radius is going to be equal to tangential. So 1.3 times negative 0.695, we get a tangential of 0.9035 meters per second squared. So a cool way of authenticating this is with my accelerometer app. So that's how it looks like. What I'm going to do is put this on my back, do a push-up when it started, and we're going to see the maximum acceleration associated in the z direction so we can figure out that tangential acceleration. Alright. So starting from here, boom. Okay, so as you can see, the max here in the z column was 0.859, which is very close to our value of 0.9035 meters per second squared, so we're pretty accurate. Alright, finally, I know I'm over time, but I want to talk about the work done, which we know is the change in kinetic energy, which in this case is going to be 1/2 I angular velocity squared. So that's the final minus the initial. And that comes out to negative 38.2 Newton meters, which is actually very close to our net torque of negative 39.5. So I have a feeling that these two are related. So finally, my test question at the end: what is the source of the work that's being done here?